So 11.7, it's going to be a 2-day event again. First day is we're going to work with changing rectangular to cylindrical coordinates. Tomorrow you're going to do rectangular to spherical coordinates, okay? In 3D world, having a variety of different ways of representing a point is so important because some ways of representing are a lot cleaner and easier to understand than others, okay? Rectangular would be really good if you want to describe a box in 3D. Cylindrical would be really good if you wanted to describe a cylinder or something that spins around an axis. And spherical obviously would be really good if you want to describe spheres. Okay, so they can all be all surfaces can be represented in all three categories. It's just which category is easier to deal with. Especially envision this in a couple chapters when I start asking you to take derivatives and integrals involving these shapes. So an important graph to understand for you guys is on page 804. And not really a graph, it's more of a diagram, page 804. If you can draw this, you will be just fine in always relating formulas between rectangular, cylindrical, and spherical. Okay? So the y-axis, the z-axis, the x-axis. Okay? And I'm going to come out and put a point right there, and this is going to be my x, y, z point. Okay? So out of the board to the right and then up. Okay? I might erase this back line because you don't really need it if it's all up in the front, and you don't really need that part either. Okay? So that same point defined in cylindrical is, you've seen this guy before, it's r theta z. Now the nice part about this is you have done in 2D, you have done things into polar. You've changed x's and y's into r's and thetas. You already know this section then, because all you're doing is changing the x and y's to the r theta, so you're doing the 2D representation of changing rectangular to polar, and then you get to keep the z's the same. So basically, cylindrical is polar plus the z component, okay? And so the polar part is kind of sharing the projection of this red dot where it lands on the xy plane, and then the z just elevates it back up, okay? So with that in mind, let's see if we can remember our calculus with how to change x's and y's to r's and thetas. Okay? I'm going to first draw a blue line here onto the ground, and I'm going to draw in and highlight this triangle. Now it looks like a normal little triangle, but you got to realize that this is 90 degrees. So if it's 90 degrees, that's nice to know. This was the x. All the way out here was the y. And r is the radius from the yellow dot here on the ground to the origin. So there's the r. So if I have the x, the y, and the r, and it's a right triangle, I know it looks like the y should be the hypotenuse, but it's not. In that, then, you would have x squared plus y squared equals r squared. That's a guy you need to know. Okay? And this is taking me from rectangular to cylindrical. Okay? Now, the angle that we used to always describe, think back into 2D world. Here's x, here's y. If I gave you a guy here, this is x comma y. And if I wanted to change it to r comma theta, this was the r, and the theta came away from the x-axis and towards the y-axis. So away from the x-axis and towards the y-axis would be right there. That is the theta. Okay? So let's look at that theta and what call would it be. And if you guys don't like that triangle, if you want, I can redraw this triangle and make it just a little bit better orientation. X, Y, there's the 90, there's the theta, there's the R. So how can I refer to the theta based off not the R, but the X and the Y? And you can say tangent theta is Y over X. Okay? So now I've changed the R to C. For the X's and Y's go to the R, and the Y's and X's can also go to the theta. And the nice thing about this is the Z is the Z. So there's no transformation of the Z to the Z. Okay? So that's one way. That's how you go from rectangular to cylindrical. But I also might ask you how to go from cylindrical to rectangular. Okay? So cylindrical to rectangular, I want to use the R's and thetas to get the X's and Y's. So one call using R's and thetas is you could say X equals cosine theta, R cosine theta, and Y equals R sine theta. That's just trig calls. And then if I needed the Z, I have the Z again is still the Z. So from this picture, I was able to help define for you the cylindrical coordinates and their representations and how to get formulas from it. I don't remember the formulas unless I've been doing it over and over for a couple days in a row. But let's say 2 weeks from now I have a test and I kind of forget it. I draw the picture. And the picture is pretty simple right now. Just wait till I add on the spherical coordinates for tomorrow. Okay? So we're going to take a look at one where I go from rectangular and I want to change it to cylindrical on the next page. Okay, so let's just see if we can plot the rectangular 0, 5, 8, get the cylindrical, and then let's see if we can actually get it with formulas as well. So plotting, because I gave you the 0 here, it's pretty straightforward that I didn't go anywhere on the X. I went over 1, 2, 3, 4, 5 on the Y, 1, 2, 3, 4, 5, 6, 7, 8 on the Z, and there I am, 0, 5, 8. Okay? Now, right away, if I want cylindrical, you know it's an 8. Okay? The Z is the Z. Okay? Now, I want that length. That length is how far... Oh, that's badly drawn. That is really badly drawn. My fault, guys. I want... let's just do this first, and then I'll show you where that length is. X squared plus Y squared equals R squared. 0 squared plus 5 squared equals R squared. So R equals 5. Because remember, I want the length... If this fell down to the ground, how far away is it? And that is a 5 on how far it is away from the origin when it fell to the ground. So do not think of R being from the origin to the dot itself. It's the radius on the ground. Again, take a look at my picture. It's the radius on the ground when that red dot falls down to the ground. So when I brought that green dot down to the ground, it landed right there, and the radius there was 5. Okay? And now the angle, visually remember, it comes off of the X going towards the Y. So it's here, but then it is how much rotation did I do until I get to that point. And if you see it, I swoop through all the way from here to there, which is 90 degrees. Okay, so that would be 90 degrees. And you could see that by saying tangent of theta is y over x. Tangent of theta is 5 over 0. When is tangent of theta undefined? And visually, that's at 90 degrees, or probably better yet, you might also want to get used to calling it 5 pi over 2, 8. Okay? So when you walk on x, y, z, you walk out on x, over on y, up on z. Cylindrically, though, you don't walk that way. You kind of walk based off the angle first. Set up your angle. So turn your body at the origin, and this is where it would be nice if I was in class instead of on a video lecture. But you would move your eyes from the origin away from the x-axis until you hit the correct angle. Then you would walk that r distance, so in this case 5, and then you would look up the z to go up 8. Okay? So let's look at another one. Okay, rectangular 7, 6, 8. Let me see if I can try this again. It's easier visually, but let's see if I can visualize it for you this way. 7, 6, 8 would be this. Out, 1, 2, 3, 4, 5, 6, 7. Over, 1, 2, 3, 4, 5, 6. Up, 1, 2, 3, 4, 5, 6, 7, 8. That's how you walk rectangularly to 7, 6, 8. Okay? Cylindrically, think of your eyeballs, okay, staring through the x-axis, and you need to change your eyeballs. You are rotating yourself until you're looking that way. So you're making your eyeballs look that way, and you care about the angle that made you do that, so you rotated your eyes that way. Then you're going to walk that direction, the distance r, and then you're allowed to look up the distance z. That's kind of the metaphor of how you walk out rectangularly on the red and cylindrically using kind of my green, blue, black. Okay? And you can imagine Nate Bach doing some crazy walking thing to help you with that. And I can do that next week if you want. So, formula-wise, if I wanted the r, x squared plus y squared equals r squared. So 7 squared plus 6 squared equals r squared. 49, 36, 49, 36, 85 equals r squared. R equals square root of 85. Done. Angle. Tangent of theta equals y over x. Tangent of theta equals 6 over 7. Theta turns into about 0.7 radians, or 40.6 degrees. So that's the amount of movement with your eyeballs, and then you looked up. So your options are, you either would say square root of 85, 0.7, and I looked up 8, or square root of 85, I rotated 40.6 degrees, and I still looked up 8. And so again, order-wise, when you walk this out, you do this first with your eyeballs, then you walk that distance, and then you look up that way. So for me, sometimes I kind of wish it was theta r z, because that's the style you actually walk it out on. So right now, all we've done is look at changing points to points from rectangular coordinates to cylindrical coordinates. I have not talked to you at all about equations. So I want to show you here, cylindrical equations do great for surfaces of revolution around the z-axis. Now this is equations, not points now. So I'm not just talking about coordinates. I'm looking at actual equations. So that guy definitely rotates revolves around the z-axis, and it's super boring. Every time you rotate this or revolve it, what is the r? Every single time the r is 5, because it's that circle with radius 5 every single time. So if you take a look at this, you have r squared equals 25, so r equals 5. R equals 5 in Calc 3 gives you that cylinder, okay? Because I do not restrict at all the theta, and I do not restrict at all the z. So no restrictions on theta or z, meaning theta can rotate as much as it wants between 0 and 2 pi or more, okay? And z means you can go forever up or forever down. That builds that whole cylinder, okay? Let's take a look at another one. Here is a bowl, okay? It's that elliptical paraboloid, okay? And what I'm telling you is z equals y squared is my trace. And then I start revolving it around the z-axis, and that makes my circles. So if that makes my circles are all about x's and y's because you smash it down onto that ground. So x squared plus y squared has to be some sort of radius in terms of z squared. The reason I had that is because I can solve this and say y equals the square root of z. So I can have that. That turns into x squared plus y squared equals z, which means r squared equals z, which means r equals the square root of z. And that right there defines the elliptical paraboloid. Instead of the x squared plus y squared equals z, it drops right down to that. Again, because you have a surface of revolution around the z-axis. Another one. Spins on top, spins on bottom. I have an elliptical cone. Again, if you look at this, this here is y equals z or z equals y. That's what I gave here. And I spin that. And again, that also goes down into the other bottom left section. And I can spin that. So I have x squared plus y squared equals, it's z squared, but you might want to think of it as z, that's my radius function, squared. So when I simplify, I got x squared plus y squared equals z squared. R squared equals z squared. So R equals z. What's kind of neat about this is what it's saying visually is this. If I go up to, let's say, 5 on the z, what's my radius? 5. Let's say I go up to 10 on the z. What's my radius? 10. Now, we might want to fix this real quick. If I go down, let's say 6, down -6 on the z, what's the radius? It's actually 6. So when I do square roots, you know how you get the plus or minus? Well, I might be a little bit more specific here and say the radius always has to be positive when you spin these. So the radius is the absolute value of z. That is the exact same form for an elliptical cone in the cylindrical way. Okay? And I got one more here. That's a hyperboloid of one sheet. Okay? So I just gave you a basic one here. Since I gave you a 1, that would mean that the radius for the origin is 1. And when you spin this out, there's circles all along the z-axis. That's why you have the x squared plus y squared. So when I try this, I can say x squared plus y squared minus z squared equals 1. So let's say x squared plus y squared equals z squared plus 1. X squared plus y squared is r squared. Is z squared plus 1. And now you have it in terms of r's and z's. which is again cylindrical. And let's do one more slide before we call it good today. Oh, actually not. 2 more slides. Sorry about that. So it's actually really good. Cylindrical helps you a lot when you revolve around the z-axis, but it also helps you with a couple specific planes. The planes I'm referring to are the horizontal plane. Any horizontal plane is really nice to say in cylindrical. And you might go, well, that's dumb, because it's really nice to say in rectangular as well. So let's say I go up to level 5 and I have a ceiling. What's true everywhere? Every single place on this, x's and y's change, but the z stays the same. So that's really nice in cylindrical, but it's also really nice in rectangular because it's the same thing. Z is z in either one. But the one that's really nice is a vertical plane through the origin. Okay, so let's see if I can draw that for you. So it would be a guy that, okay, that dot is on it, okay? So that plane could be a little bit harder to describe with x's, y's, and z's, but with your eyeballs, remember your eyeballs first look this way, but then it needs to turn this way, and that's your angle for your eyeball. Well, everywhere on this plane, dot, 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 the x's change, the y's change, the z's change. You could argue the r's change because any dot, when it falls down, has a different length back to the origin. But what never changes? The theta. Okay? The theta is always the same. Okay? So if you give me what that theta is, let's say I gave it to you as 45 degrees, you know exactly what that plane is. It means every single dot that's allowed to be at the angle 45 degrees. So more generically, if you give me a number, it defines that plane. Okay? Last thing, okay, last problem, and then I'll close up shop, is here. Let's take a cylindrical to rectangular equation, okay? So it's nice sometimes to be able to bounce back and forth between, it's nice to bounce back and forth between what a cylindrical equation looks like and a rectangular equation looks like. So this guy here, I have no idea what it looks like, so it might help me to see what it is in rectangular. I taught you how to change r's, I taught you how to change z's, I taught you how to change thetas, or better yet, cosine thetas or sine thetas. I did not teach you at all how to change cosine 2 thetas. And if you're going, what are you saying, Bach? Look back here. This is all about cosine theta or sine thetas. It's nothing about 2 thetas or sine 2 thetas. So on here, I don't want this guy like that because I don't know how to change it between rectangular and cylindrical. So we got to use one of these 3 double angle formulas. And it does not matter which one you use. Okay? The top one, you're probably going to be changing things with an x and a y. The middle one would be all about x's, and the bottom one would be about y's. Me personally, I would not use the top one because I don't want to add x's and y's to the story. I'd rather just add one of them. So let's change it based off of this. So I could say r squared 2 cosine squared theta minus 1 plus z squared plus 1 equals 0. Okay. So now with that, I could distribute 2r squared cosine squared theta minus r squared plus z squared plus 1 equals 0. Okay. From there, let's see what I have. Notice, if I rephrase this, 2r cosine theta squared minus r squared plus z squared plus 1 equals 0. If I do that, you might see a lot easier that r cosine theta, that is x. So I got 2x squared minus x squared plus y squared plus z squared plus 1 equals 0. So that's x squared minus y squared plus z squared plus 1 equals 0. Hey, this is starting to look a lot more like a shape that you do know. I would probably rearrange a little bit and say x squared minus y squared plus z squared equals negative 1. Divide by that negative 1, and I got negative x squared plus y squared minus z squared equals 1. You need to know what that shape is. It has two negatives. Two negatives. So it is the two-sheeter. It opens up on the y. Opening up on the y because that guy's the positive. So if you want to figure that out, you can say y squared equals 1. Y equals plus or minus 1, meaning over 1, left 1, and I start creating my circles. And there's one sheet and two sheets. So in this case, the top guy was super ugly. I had no idea what this looked like in cylindrical coordinates. But transferring it, it actually looked nicer or more familiar to you in this form. So being able to switch between rectangular and cylindrical is very important. Likewise, from cylindrical to rectangular. And next week, I'll add in the spherical. Here's your homework. Sorry I've been gone again, and I will see you on Monday.